Find all complex-valued functions f such that for all integers a, b, and c that satisfy the equality a plus b plus c equals 0, the equality shown on the screen holds. We'll use different combinations of integer numbers a, b, and c with zero sum that will help us to figure out how the target functions look like. We will call target functions that satisfy the conditions of this problem simply valid functions for short. This process will resemble the sport of rodeo. We will round up the target functions, we'll throw lasso on them, and we'll bring them to the corral. Clearly, if function f is a valid function, then the same function with coefficient d, where d is any complex number, is also a valid function. It means that for each valid function f, if f of 1 is not 0, there is such a coefficient d that's equal 1 over f of 1, such that function df has value 1 at the argument 1. Thus, we can assume, without loss of generality, that any valid function has value f of 1 equals 1, with the only exception when f of 1 equals 0. I have come up with another equality that is equivalent to the given equality, which is easy to verify. We can occasionally use this second equality as well as the original one. The most simple triple of integer numbers with zero sum is 3 zeros. Let's plug the value f of 0 into the second equality. This helps us to discover that for any valid function f, f of 0 equals 0. We can use this result to find another important property of each valid function f. If we use a valid triple a minus a0, where a is any integer number, and plug it into the second equality, we can easily see that f of a equals f of minus a. Now we can use such triples where one number is equal to the sum of two other numbers, as well as the triples where one number is equal to negative sum of two other numbers. And from now on, we can consider only positive integer numbers and 0, since a valid function has the same value at any negative number as at its symmetric positive number. Let's assume that some positive integer number a is a root of a valid function f, and b is another integer number, and we'll plug the triple a, b, and a plus b into the second equality. If a positive integer number a is a root of function f is periodic with period equals to a. And in this case, function f has constant value in each subset of integer numbers that we call congruence class modulo a. There are exactly a such congruence classes, where each class consists of the numbers that have the same remainder after dividing it by a. Next, we'll discover the critical rules for values of each valid function f at even integer numbers. For that, we'll plug a triple consisting of a, another a, and 2a, where a is any positive integer number. Another small dosage of simple algebra reveals two rules. The value of function f at even integer number 2a must be either 0 or 4 times the value of this function at number a. Now we can for the first time throw a lasso on the first horse, that is, the first valid function. We'll apply rule number 1 to the lowest even number 2, so that f of 2 equals 0. As we know, such function is periodic with period 2. The value of this function at all even numbers is 0. and its values at all odd numbers are equal to f of 1. For example, if f of 1 is 0, then function f is constant 0 at all integer numbers. It's easy to verify that this function is a valid function. If three integer numbers a, b, and c have zero sum, or one of them is equal to the sum of the other two, then either all three numbers are even, or two of them are odd and one is even. In both cases, the equality of this problem holds. Now we will apply rule number 2 to the lowest even number. If we assume that f of 1 is 1, then f of 2 is 4. And from the mere fact that f of 2 is 4, and from the original equality, we will obtain a recursive formula that will show how such function's value at argument n plus 2 depends on its value at argument n for any positive integer n. For that, we will plug the triple consisting of number 2, number n, and number n plus 2, where n can be any integer number, odd or even, into the original equality. It results in the quadratic equation where f of n plus 2 is the variable that we want to express in terms of function's value at number n. The standard formula for the roots of quadratic equation leads us to this recursive formula. This formula can produce two different values for each n, either with plus or with minus sign in its expression. Let's examine both possibilities. Suppose that this formula has plus sign for all positive integers n. Then the only possible function that has this property is f of n equals n squared. Since for the first argument values 1 and 2 and 0 as well, this formula holds, we can prove it using the method of mathematical induction. If we prove that under assumption that it's true for argument n, it is also true for n plus 2. By looking at this formula, we see that it's obviously the case. We can verify that this is a valid function if we plug in this function's values, a squared, b squared, and a plus b squared, for any two numbers a and b into this problem's equality. You can prove as a homework that this equality holds for any such two numbers. And this will tighten the lasso on the neck of the second horse. Let's review what we got so far. The value of any valid function at number 0 is always 0. The value at argument 1, we can assume without loss of generality that it's equal to 1. The case f of 1 equals 0 yields only one trivial valid function, that is constant 0. We have examined the case f of 2 equals 0, which yielded one type of valid functions in case 1. Then rule number 2 leaves only one possible value for any valid function at argument 2. It's 4 times f of 1. Thus, in all the remaining cases, we can consider the values of all the valid functions at the first integer numbers 0, 1, and 2 fixed with values 0, 1, and 4 respectively. We have also discovered the recursive function that describes all our valid functions when f of 2 equals 4. Let's apply this recursive formula to numbers 0 and 2. We can see that both signs, plus and minus, produce the same result, f of 2 equals 4. Let's assume that number n plus 2 is the first such positive integer for which the recursive formula has minus sign, so that for all integer numbers from 1 to n, the formula f of n equals n squared holds. Clearly this is true for the first two positive integers 1 and 2. Let's assume that the first such integer is odd and has form 2m plus 1. That implies that function value f of 2m is 2m squared and f of 2m minus 1 is 2m minus 1 squared, which yields the formula for function value f of 2m plus 1 equals 2m minus 3 squared. If we plug the valid triple 1, 2m, and 2m plus 1 into the problem's equality, then we'll get the equation, which after simplification gives us the quadratic equation 8m squared minus 3m plus 4 equals 0. This quadratic equation doesn't have any real roots, so that this case is impossible. Assume that these two numbers are 2m and 2m plus 2. And 2m plus 2 is the lowest number for which the recursive formula has minus sign, and therefore the value of function f at argument 2m is still 2m squared. So the value of function f at 2m plus 2 equals 2m minus 2 squared. Let's examine subcase A, in which this function value is not 0, just like it is for the first even numbers 0 and 2. Now, since we know that f of 2m plus 2 equals 2m minus 2 squared, and if it's not equal to 0, then it equals 4 times m minus 1 squared. On the other hand, if you apply rule number 2 to the value f of 2 times m plus 1, then this value is supposed to be 4 times f of m plus 1, which implies that m plus 1 squared must be equal to m minus 1 squared. And that is only possible if m is 0. But the case m equals 0 only gives us f of 2 equals 4, which we already assume. So this is really not a new case. The last case we haven't examined yet is the subcase B of the previous case. It's when our recursive formula with a minus sign is applied to the even number 2m plus 2, and in this case it's also equals 2m minus 2 squared, but now it's equal to 0. The formula 2m minus 2 squared equals 0 is possible only if m equals 1, and that produces the equation f of 4 equals 0. This is the new case. If 4 is a root of function f, then f is periodic function with period equals to 4, which implies that all integers multiple of 4 have the value of function f equal to 0. All integers 4m plus 1 have constant value of function f equals to f of 1, and all integers 4m plus 2 have constant value equal to f of 2, which is equal to 4 f of 1. We need to examine the values of function f at integers 4m plus 3. Since number 6 belongs to congruence class 4m plus 2 modulo 4, its value of function f is 4 times f1. On the other hand, since f of 6 is not 0, it must be 4 times the value of function f at number 3. So the value of f at number 3 equals f of 1. Therefore, the entire class 4m plus 3 has constant value f of 1. Now definitions b and d can be combined into one definition b. All odd numbers have constant value f of 1. And also, if f of 1 equals to 0, then the entire function is the constant 0. We can quickly verify that the function that we have just defined is a valid function. We can examine all the possibilities of numbers a, b, and a plus b. All these three numbers can be multiple of 4. Two of them can be from congruent class 4m plus 2 and their sum multiple of 4. We can have two odd numbers and their sum 4m plus 2. And the last possibility, two odd numbers and their sum multiple of 4. We can easily check that in all these situations the equality of this problem holds. To summarize our findings, we have discovered three types of valid functions. The first type is a periodic function in which all even numbers are roots. The second type is a periodic function in which all multiples of 4 are roots. And the third type is the quadratic function n squared times the value at argument 1, which can be equal to any complex number. By reviewing our cases, you can check that these three types represent all the functions that meet the requirements of this problem. We have really covered all the bases. But wait, this is a metaphor from a different sport. Okay, we have brought all the horses to the corral. And we should say, yeehaw!